Alright, so you might be asking yourself, what in the world was that exercise all about? Number 6. So in number 6 we were showing that if you define W as the span of the k plus first to the nth eigenvectors of A transpose A corresponding to the eigenvalues being 0, then that W is actually the null space of A. Okay, and why is that important? That's important because what we want to talk about now is how the SVD tells you about the 4 fundamental subspaces. So the SVD and the 4 fundamental subspaces. I already gave away the punchline before, but let's go ahead and walk through it again. So the 4 subspaces for an m by n matrix A look something like that. And so our domain is Rn. If A is m by n, the range is, or the codomain is Rm. This will be the null space of A down here, and this will be the row space of A. This will be the column space of A, and the null space of A transpose. Good. Now A is U sigma V transpose, right? And so if the rank of A is equal to K, that means the dimension of the column space and the dimension of the row space are both K, right? Good. Now the U's, remember that the U's are in Rm, the columns of U, and the columns of V are in Rn, right? So the V's are over here and the U's are over here. Yeah. All right. So also I want to emphasize that in sigma, the sigmas are ordered highest to lowest. That's very important. Okay, that means that the first k of them correspond to the first non-zero, or I should say all the non-zero sigmas. Good. So what did we say? We said that the null space of A was equal to vk plus 1 through vn. Well, that forces the rest of the row space to be spanned by the first k vectors of V. Good. Now the column spaces of A is also k-dimensional, and the U's are in order, and so the column space of A is the span of U1 through UK, and so the null space of A transpose then is spanned by UK plus 1 through UM. Good. And so this picture right here is the reason that the SVD is so important, because it tells you everything you need to know about the 4 fundamental subspaces in explicit detail. In other words, if I compute the SVD for a matrix A, then it's easy to formulate a basis for all the vectors for each of the 4 fundamental subspaces. Good. Now, why would this be? Oh, by the way, there is something else I might mention, the reduced SVD. So for example, suppose that A is like 5,000 by 3. Well, if I try to take the SVD itself, right, the U matrix would be 5,000 by 5,000. That's a huge matrix. And in fact, you can imagine that 5,000 is not very long for a matrix like this. It could be, 50,000, 100,000. This blows up the amount of space we need to compute the SVD. So instead of doing the entire 5,000, what we can do is, if this is 5,000 by 3, then we could just write that A is equal to U, and I'll just take the first 3 columns. I'm kind of using MATLAB notation there. And then for the sigma, I would just take the first 3 values, and then I'd multiply that by the first, or I'd just keep the first 3 columns of V as well. Good. And so this is an example of the reduced SVD. Okay, so if M is bigger than N, so that we have a tall matrix, the reduced SVD that the computer is going to work with, reduced SVD in software, is typically going to be U sigma. I'll put tildes over the top because U tilde is just going to be the first, using the first n columns of U. So it's not going to be the full U, it's just going to be U with the first n columns. And then this is just going to be your sigma with 1 to n, 1 to n. And then your V is just going to have the first n columns. Okay? So keep that in mind. Now what I will typically do is when I talk about the reduced SVD, and you'll know which one you're talking about. If you're not sure which one I mean when I say reduced SVD, just ask. But if A has rank K, then we can write down the reduced SVD as U being M by K, and then, whoops, sigma would be K by K, so that's square now, and then V would be N by K. Okay, and so those would be our reduced SVD matrices. Okay, now I should say that some books will call this reduced SVD up here, they'll call this the thin SVD. That's the Golub and Van Loan version. They're kind of the, they wrote basically the Bible of numerical linear algebra. So if you ever have a question about numerical linear algebra, look up their book, Matrix Computation. It's a classic. They call this the thin SVD. That's why I kind of gone to other language for this. I call this the reduced SVD, although the software companies have decided that that's reduced SVD too. So yeah, be sure you know which one you're talking about. It's either k dimensional, which is the rank, or n dimensional, which is the lesser of m and n. Well, m is greater than n, so in this case. Good. Okay, that's just a kind of a side note, because you don't typically want to compute the full SVD. By the way, I should say it's really obvious when you see that A, using this decomposition, you can write A using that the little outer products. And so instead of writing this out as a matrix product, you can actually write this as sigma 1 U1 V1 transpose plus, I better write down a few more, sigma 2 U2 V2 transpose plus plus sigma k UK VK transpose. And I'm going to stop here because everything else would be 0, right? Because the sigmas would all be 0. And so it doesn't matter that you include those vectors or not. And so that's why I say this is usually as far as you need to go, the first k values. Because the rest are contained in the null spaces. Unless you're looking specifically for null spaces, I would say you don't really need that stuff. Okay, good. So, excuse me, I've made a couple of notes in the, or I've made a couple of comments in the notes about programming with the SVD. So you should take a look at those and try them out. Whichever flavor you want, MATLAB, Python, or R. And I think because we're already at the 9-minute mark, I may stop here, and I'm going to put together a few exercises and applications of the SVD. So there's two main applications that we're going to look at. Two main applications. One is going to be the generalized inverse. And number two, we're going to have some fun with some image processing. Okay, and so that'll be Friday. All right, I'll see you then.